Hi everyone, so let's start. The speaker for this session is Professor Ingo from the Rutgers University at Newark, who is also the recipient of the Frontiers of Science Award. So today he will tell us a story about uniform estimates for complex point, unpacked, and fully nonlinear equation. Please.
Thank you very much. Thanks very much for the introduction. Well, it's my great honor to be here to explain some very recent results on the uniform estimate for complex Monge-Ampere equations and also for the more general fully nonlinear partial differential equations. And this is based on a series of journal works with Phong and F. Well, my talk is going to consist of 3 parts. First, I will explain some background, and then I'll state the main result. Finally, if time permits, I will mention something about the outline of the proofs. Well, so first, let me fix some notations that I'm going to use throughout the talk. Well, I'm going to denote X as a compact complex manifold without a boundary, and we always assume the complex dimension of the manifold is n. And here, omega is supposed to be some kind of emission metric, just like the Riemannian metric, but this time we express the metric in under a local holomorphic coordinates. And under such coordinates, we can express the omega by local matrix value of the functions Gij, Gij bar. I just distinguish the indices with bar or without bars. Well, those Gij bars are locally defined functions, which at every point it is a positive definite emission matrix. Well, here omega is said to be Kähler, meaning that the one form written here is actually declosed, meaning that in local holomorphic coordinates, it has a very simple expression for the Kählerness. It's that the ordinary derivatives for the components Gij bar in the direction of zk, this is a symmetric for the indices with bars or without bars. So this is a condition of the Kähler. And for the Kähler geometry, a very useful thing is that the Ricci curvature for the metric coincides with the Riemannian curvature. And it has but for Riemannian curvature, we know the expression is really, really complex. But the Ricci curvature for the complex, especially for the Kähler metric, has a very simple expression in terms of the second order derivative of the volume or the volume coefficient of the metric up to a certain sign. So this gives us the many benefit for working in the category of Kähler geometry. Well, by the way, the Ricci curvature defined in this way automatically must be closed. So it defines some cohomology class, and this cohomology class is canonical in the sense that it is a smooth representative of the first term class up to a certain sign, a certain multiple constant. So this is going to be our notations. And one of the major questions or problems in Kähler geometry starts from Calabi in 1950s. Well, just from the previous slides, we have seen that for any given Kähler metric, its Ricci curvature is a natural representative of the first term class. So Calabi asked the converse question. So given any representative in the first term class, can we find a Kähler metric in any given Kähler class such that the Ricci curvature of this metric is exactly equal to the previously given smooth representative gamma? While Calabi himself already proves the uniqueness part of this his conjecture. That is, whenever there is some metric omega prime in the Kähler class, then it must be unique. But the existence part is at least in the 50s or 60s is assumed to be the most difficult part for this proof for this conjecture. Well, it was Professor Yao who first solved completely this conjecture, and he showed that we also have the uniqueness. Oh, sorry, we also have the existence for such for this conjecture. Well, in particular, an immediate consequence of Yao's solution is that if the first term class is 0, then we always have Ricci flat matrix in any Kähler class on the manifold. Well, let me mention something about the reduction of Calabi's conjecture to the fully nonlinear. For this is a very important type of fully nonlinear equation. This is a complex Monge-Ampere equation. Well, an advantage of Kähler geometry is we have the DD bar lemma. DD bar lemma for I just state the DD bar lemma for this special case of 1-1 classes. The DD bar lemma says that if we have two cohomology classes of in a given Durham cohomology class, we have two smooth representatives, then the difference of them must be a DD bar exact, not just the D exact. Well, say we know that for the gamma, the previously given smooth representative of the first term class, and the Ricci curvature, they belong to the same class. So the difference is the DD bar of some scalar valued function. We assume everything is real, so this function f is can also be assumed to be a real valued function. And f is well defined uniquely only up to addition of some constant. So we normalize the function f so that its integral equal to the total volume, just a convenient normalization condition. Well, given the DD bar lemma, we know that any Kähler metric in this Kähler class is given by the form of omega plus DD bar of phi. And well, in fact, this just arranges over all the smooth Kähler metrics in this Kähler class. Well, suppose this omega phi satisfies the Calabi conjecture, that is, satisfies this required equation, then we can verify by using the definition of Ricci curvature and also this identity that the metric omega phi satisfies this nonlinear equation, fully nonlinear equation. Omega phi, by definition, by my notation, just this given by this 1-1 form, is nth power. Well, I use the power means the Weijian product. Is nth power equal to the prescribed function e to the f. Well, so the solution of the Calabi conjecture now reduces to the solvability of this complex Monge-Ampere equation. Well, to prove this, to solve this fully nonlinear equation, Yau's original method is to run this continuity method. So this is what he did in the 70s. That is, you start with the given function f, and we consider a family of equations with the parameter t in the unit interval, and we multiply f by t and then add a normalizing constant ct on the right hand side, and we consider this family of complex Monge-Ampere equations. Well, to run the continuity method, we define a set I by the times s at which this equation admits a unique solution. Of course, I have normalized the equations to make the normalize the solution phi t to make the equation uniquely solved if it admits a solution. Well, we set this I to be the solution set, that is the times when this equation is indeed solvable. And this set, of course, is empty, is non-empty, because at the point 0, at time 0, phi t constantly equal to 0 is just a trivial, well, an obvious solution of this equation. So it's a non-empty set. Well, from topology, we have known that if we can show that this set I is equal to the full interval, then at time t equal to 1, we just get the solution of the desired Monge-Ampere equation. Well, to show this set I coincide with the full interval, we have first to verify it is non-empty. And next, if we can show that this, the openings of this set is also not a difficult task. It's open by using the implicit function theorem. Just to consider the linearized operator of this associated to this fully nonlinear equation. But the hard part is to show the closeness of the set I. Well, assuming that we can show the set I is open and both open and closed, then the interval, the unit interval is connected, so it must be the full. This I must be the full set. So we only need to show I is the closest set. Well, the closeness follows from many a prior estimates, and this is the hard part. Well, assuming the C0 estimate, let's assume that the phi t is uniformly bounded in the C0 or infinity norms. And then the C2 estimate originally was due to Yao and Orban independently by a very clever application of the maximum principle argument. And for the higher order or C3 and higher order estimate, it follows originally from Yao's Calabi C3 type estimate. And later on, there is the more powerful Evans-Krylov theory for the fully nonlinear concave differential equations. And for the complex Monge-Ampere equations specifically, Phong, Sesam, and Sturm, they found in 2008 or 2006, they found a very simple approach, which give the C3 and also higher order estimate for specifically for the complex Monge-Ampere equations. Well, the C0 estimate turns out to be the most difficult and challenging part for proving the a priori estimate. Well, originally Yao uses and develops the Moser iteration argument to do this job, and so he proved that completely solved the complex Monge-Ampere. But this is just a very brief outline of the approach. It's quite involved. Well, motivated by the recent interest from geometry, from algebraic geometry, it is very necessary to consider not just the smooth equations, but also the singular, more singular differential equations. Here the singular means the function on the right or the volume form may have some pole or zeros. Well, for example, this is the most, I think this is the simplest singular Monge-Ampere equation in Euclidean geometry. We just put a pole, a very small pole, on the right-hand side. Well, assuming that this beta is not so bad, then Yao's Moser iteration argument can give us some C0 control of the solution for this kind of equation, for this kind of solution. Well, but by the way, I just want to remark that this type of equations actually give the conical Einstein tap equation, Einstein tap kilometrics, which plays a very important role in the resolution of the YTE conjecture of Donaldson, and so on. Well, motivated by the classification of singularities in birational geometry, it is very important to consider this more general fully nonlinear Monge-Ampere, more general Monge-Ampere equations. Well, luckily, after Yao's theorem, original proof of the C0 estimate, we do have a very general and satisfactory results, which was due to a Poland mathematician Professor Calabi, who showed that we only need the function on the right-hand side to be slightly better than L1. We only need it to be integrable in the sense of L1 plus epsilon for any positive epsilon. Then immediately we will have the C0 estimate for the solution phi. Well, Calabi himself not only showed the L infinity or C0 estimate of such a solution, he also derives some Holder continuity, uniform Holder continuity of the solution phi whenever the function on the right is in LP, for example, p bigger than 1. And I also want to emphasize that this his estimate is actually sharp, in the sense that you cannot replace the p strictly bigger than 1 by p equal to 1. There's a very classical counterexample. This is a so-called pluripotential function, which has a log pole, and you can verify, or you can just smoothen it a little bit and globalize it a little bit. You can verify that this Monge-Ampere Monge-Ampere associated to the Poirier-Green function is like a delta function at some base point. But this guy is not L1. This guy is not bounded. It has a log pole, and it belongs only to L1. So Calabi's result in some sense is sharp. Well, Calabi's original proof relies heavily on the pluripotential theory developed by Bedford-Taylor in the 1970s and 80s. And this is a very powerful tool in complex analysis to deal with the derivatives or the Monge-Ampere operators for bounded, maybe non-smooth Poirier subharmonic functions. Well, Calabi's approach also has this benefit that it can be also adapted to the setting of degenerating background metrics in the following sense. Say, if we have the reference, if we deform the reference metric omega t in a bounded family to some limits, to some non-negative limit, then in some sense, as long as we have the control of the right-hand side in some LP sense, then we will still have the uniform L infinity estimate for the solution phi t. Well, more precisely, I'm going to give you at least one geometric setup. Suppose we have a bidirectional holomorphic map from some manifold, Kähler manifold to another Kähler manifold. Possibly the metric may degenerate, and we consider the pullback of some Kähler metric downstairs, and they will perturb it by adding some positive part to make it Kähler. And then we consider this a family of complex Monge-Ampere equations with a reference metric omega t degenerating to this pullback of some Kähler metric downstairs, which is only a smooth 1-1 form. It may degenerate along some very large set. Well, for this complex Monge-Ampere, this family of complex Monge-Ampere equations, here's, by the way, this is CT just a normalizing constant to make sure that the L1 norm of the function e to the ft is uniformly bounded. Well, by developing the approach of the original approach of Calabi, two groups, Azadil, the Gadget-Zarrahi, and Monge and Pali, they independently obtain this family version of Calabi's sharp infinity estimate, which is, of course, rely heavily on the pluripotential theory. Well, the L infinity estimate for this degenerating complex Monge-Ampere equations are very useful. Is in some sense crucial for obtaining any geometric features of the Kähler matrix. Well, let me just mention some applications. Well, it's just a very limited application. Well, I just mentioned very limited ones. Those, for example, to those study of the Kähler-Ricci flow, and also in the study of the generation of a Calabi matrix in the works of Tosadian and Zhang and Yang Li, for example. Well, so far this sharp version or the uniform version of the L infinity estimate relies heavily on the pluripotential theory. But the pluripotential theory is only available for Poirier subharmonic functions, which is specific to Monge-Ampere equations. However, by the recent development of the fully nonlinear partial differential equations on a complex manifold, it is actually necessary to study more general equations other than beyond the Poirier subharmonic functions, for which this pluripolar theory is not available. It's not so easy to develop such a theory. So a natural question arises is that is there any PDE-based approach to this to Calabi's sharp infinity estimate? And also, can we find such approach that also works for the degenerating for the family version of this differential equations? Well, there are some approaches, previously known approaches, without using the pluripotential theory. Well, notably Yau's original L infinity estimate, and also in 2011. Brodsky, he published a paper, a very short paper, using some localized ABP maximum principle, and he's able to derive the L infinity estimate for the Monge-Ampere equations when the right-hand side is only in LP, but this time P should be bigger than 2 because he need to compare this complex Monge-Ampere and real Monge-Ampere, real determinant and complex determinant. There's some gap to that. If that forces that his estimate may not be sharp. Well, both of these two approaches only work when the reference metric is fixed, and may not work. They may not even though these two approaches may not give the sharp dependence of the right-hand side. Well, a few years ago, there is a very beautiful approach developed by Wang Zhou, who proved the sharp infinity estimate for the complex Monge-Ampere equations on domains of pseudo-convex domains of Cn. Well, the keys in their approach is the Schrödinger tab inequality and also a Sobolev tab inequality for the complex Monge-Ampere operator. It's a very clever approach. However, their approach does not obviously extend to the compact case, because it relies heavily on the pseudo-convex domain. And also, it's not so easy to generalize their approach to families of differential equations. So, well, those are the backgrounds that we tried to study this problem to find a PDE-based approach for the sharp infinite estimate that not only worked for degenerating metrics, but also for the sharp dependence on the right-hand side. Well, so now we come to the main results. Well, here's my our setup. So suppose we are given a function, a smooth function e to the f on the right-hand side, divided by n, just for notational convenience. Here, little f is just some polynomial, well, not just a polynomial, some function on Rn. Here, lambda is the vector of eigenvalues of the endomorphism H phi. H phi, by definition, is the endomorphism defined by the 1-1 form G phi relative to the kilometric G. Omega is Kähler. Here I assume everything is a Kähler. Kähler without a boundary. Well, here this little f is just some homogeneous symmetric function defined on Rn. More precisely, to get some useful control of the function, we specify some convex open cone gamma, and this open cone gamma is supposed to contain the first octant and also contained in the space gamma 1. Gamma 1 is the affine upper space upper the diagonal part. That is the sum of all these lambda i's is strictly bigger than 0. Well, we also need this ellipticity, which is typical in a requirement for PDE theory. We say that the derivative of f with respect to any direction lambda I is positive for any lambda in the given cone. Well, most importantly, we have to assume a structural condition for this nonlinear function f. The structure condition essentially is the product of all those first order derivatives is strictly bigger than some given positive number gamma. This gamma is supposed to be a positive number, a positive constant. Well, this is our structural condition. Well, when we wrote the paper, we actually find a very simple criteria that guarantees this structural condition to hold. This lemma is say that whenever the function f, if we assume function f is homogeneous of degree 1 and elliptic just means the derivatives, the first order derivatives remains positive and concave. And assuming that in the first octant, the function f is bounded below by the sigma n, the product of all the components of any vector mu, then the structural condition is satisfied. So this is a very simple criteria that guarantee the structural condition. Well, for example, the Monge-Ampere equation is trivially satisfied this inequality. For the sigma k equations, this inequality is also satisfied because of this Newton and Maclaurin inequality. And notably, after we wrote the paper, Harvey and Lawson kindly informed us that all the operators F defined by some invariant guarding a Dirichlet polynomial satisfy this inequality. So this just made our just to give us a lot more examples that our theorem can apply. Well, so here's our first main theorem. I first stated for the fixed background case. So suppose phi is a C2 solution, a classical solution of the previously given fully nonlinear PDE. Then we have the uniform estimate, our infinity estimate on the solution. And this constant, upper bound constant C depends only on the given parameters. Well, MP, for this P, I need the P to be bigger than 1. I will use this kind of entropy for the function on the right-hand side. But, well, this notation, L1 log LP, is the entropy of the given function. It's just like the name suggests. It is L1 of e to the f and log of e to the f to the power p. Just the pieced integral of the function f relative to the function e to the f. So this we name this the pieced Nash-Yau entropy for the function f. Well, in case as I mentioned in the previous slide, that Monge-Ampere and sigma k operators both they all satisfy the structural conditions. So this estimate immediately covers the previously known L infinity estimate, and also is sharp because this entropy is even weaker than this L1 plus epsilon norm of the function on the right-hand side. Well, the main advantage for our approach is that it not only applies to the fixed background metric case, it also applies to the case when the background metrics degenerate to some non-active smooth one-one form. Well, so for this setup, let's assume this is the line segment. Again, just like before, I consider this line segment because this chi is a smooth non-active one-one form and perturbed by some given metric omega. And for this h phi t, it is just the endomorphism defined just like before, defined by the one-one form g phi t with respect to the fixed metric g. And I use this Ct as a normalizing constant just for write some constant on the right hand side. For most equations, we're not able to determine the constant C, but for some equations like the Monge-Ampere or Hessian sigma k Hessian equations, this Ct can be explicitly determined. Well, for this family version of the complex fully nonlinear PDE, we still have the uniform L infinity estimate. And this estimate in particular is independent of the time t. Well, the dependence of the constant C, is besides the e to the L, the entropy term on the right-hand side. Besides the entropy term on the right-hand side, we also need the constant Ct, the ratio of the constant Ct with respect to the Vt. Here, Vt is just the volume of the matrix omega t. Which is depends only on the Kähler classes. And notably, we also need just the weighted L1 norm of the function of the solution phi t. But this is not just the L1 norm of the function minus phi t, but the weighted against the given function e to the f. Well, for the Monge-Ampere equations, we know by this ratio is always 1 or just bounded, and also this energy, well, this weighted L1 norm of IT is automatically controlled by the entropy term. This just follow from the Jason inequality and the uniform integral estimate of quasi-Pluribus subharmonic functions. Well, I should give you some more remarks about the previous theorem. Well, for the previous theorem, originally we know that we also need this weighted L1 norm in the dependence of the constant C. Well, later on, we realized that in a separate paper of myself and Phong, we realized that in fact that ET, this weighted norm, can be controlled simply just by the entropy term. This is the bounded energy by bounded entropy. Entropy bounds the energy type theorem. So in fact, this ET can be removed. The dependence of ET can be removed by replacing this single entropy term of the right hand side. So this still holds for this family setting. Well, I also want to explain that actually in the previous two theorems, we need to assume the metric, the manifold itself is compact and Kähler without a boundary. Well, actually, the approach, our approach generalizes and also of course it needs some fresh new ideas. That it also works. It also works by some adaptation of the methods. The results also hold for like a much more general family, much more general category of complex manifolds. In particular, it includes the compact emission manifolds without a boundary. For such case, we still have this L1, this L infinity estimate for the solutions. But this time, the estimate may not be uniform. We have to fix the reference of the background metric omega. So the dependence is also on the reference metric omega. It's not a uniform anymore for the emission for the Monge-Ampere or nonlinear equations on emission manifolds. Well, in particular for the complex Monge-Ampere equations on emission manifolds, this L infinity estimate was first derived in the work of Winkov and Tossetti, and later on by Cycler 80 using the ABP maximum principle, and developed furthermore by Calabi, Nyon, and Dinov using the pluripotential theory. They developed this local version of the pluripotential theory. Well, for our results, we developed local comparison approach to get this estimate, which is reminiscent of our previous uniform comparison, global comparison approach in our previous paper with Freud. Well, so I guess I still have 10 minutes, so I'm going to give you some outline of the proof. Well, the major tools in the proof of the main theorem are classical ones. The first, well, everyone working in Kähler geometry knows these two basic tools. The first one is Yao solution to the Calabi conjecture. That is smooth complex Monge-Ampere equation always admits a unique solution. And second is this uniform integrability, exponential integrability of the quasi-Pluribus subharmonic functions, or this alpha invariant type estimate, which says that on a Kähler manifold, or more general on emission manifold, there is a constant that depends only on the dimension and also on the manifold itself, and the given metric omega, depend only on the upper bound of the metric omega more precisely, such that for any normalized quasi-Pluribus subharmonic function phi, normalized by the supremum to be 0, then this exponential of the function e to the phi to some alpha power is uniformly bounded. I mean, its integral is uniformly bounded. This uniform integrability of the quasi-Pluribus subharmonic functions give us a very some kind of free control on the functions. Well, the main ideas in the proof is to we try to imitate the original approach of Calabi, in which he used the capacity. The definition of the capacity is quite involved. It relies on pluripotential theory. So we try to use some kind of monotone functions that relies only on the function f, not on the capacity of some sublevel set. Here, omega s is some sublevel set depending on the solution phi that I will define later. But we do need to find first some monotone function on this s. S is just a positive number, giving the sublevel set of omega s. Well, the goal is to show that this positive or non-negative function phi of s is actually 0 whenever the s is sufficiently large, because the sublevel set is supposed to be open set. It's an open set. If we have this guy, the integral of this guy equal to 0, that forces the omega s to be empty, because it's always an open set. Well, to show this phi s vanishes when s is sufficiently large, we need to derive some effective growth estimate on the monotone function, or decay estimate on the monotone function phi of s. Well, the main idea is to introduce certain auxiliary complex Monge-Ampere equations to compare it with the original, the solution of the original fully nonlinear PDE. Well, this kind of idea, brilliant idea, originates from 1950s or 60s by the great mathematician De Giorgi, when he derived this Hanake inequality by using the harmonic function approximations. And this type of linear approximation approach has been very successful in the development of linear PDE theory. And also, for the complex Monge-Ampere equations, well, even though they didn't mention it specifically, but they have used this kind of ideas very often in the works of Calabi and so on, Tian and many others, using the complex Monge-Ampere equation as a comparison. And finally, in the fundamental work of Chen and Cheng, they combine the auxiliary Monge-Ampere equation with the ABP maximum principle to study a coupled system with the linearized equation of the Monge-Ampere equation, and this leads them to find some very important work on the CSCK, on the existence of a CSCK matrix. Well, in our part, the hard aspect is to relate the solution to the solution of the auxiliary, to introduce some auxiliary equation that is closely and cleverly related to the original solution. Well, we have to introduce some appropriate test functions to do this job, to compare the solutions. Well, the main technique in or the main outcome of this kind of technique is a Schrödinger tab inequality for the solutions. Well, this estimate just simply tells us that there is, for the solution phi of the given fully nonlinear PDE, we have this exponential integral of the solution phi over the sublevel set omega s. Sublevel set is defined to be the set where phi is smaller than minus s. Well, this estimate is in some sense stronger in the sense that exponential of the function will also take some power that is strictly bigger than 1, and this is crucial for the later derivation, in the later derivation of the decay estimate of the function, previously mentioned function phi of s. And this estimate depends also on this E of phi, this weighted L1 norm of the solution phi. Well, here let me give you a very outlined proof of this key lemma in our proof of the sharp infinite estimate. Well, we introduced the following auxiliary complex Monge-Ampere equation, and this is how we relate this is how to relate the solution phi to the solution of this auxiliary equation. Well, we use this tau k just as a smoothing of the function x times, just like this function. This function may be singular because it may have some non-smooth point at the origin, and it also may vanish somewhere. We just take a positive smoothing of this red function, which always exists. And so the right-hand side is going to be smooth. We take the constant a to make both sides of this equation compatible, just a normalizing constant. And this equation always admits the solution by Yau's solution of complex Monge-Ampere, Yau's solution to the Calabi conjecture. Well, so the next step is to relate this auxiliary equation to the solution phi, to the function phi. Well, to do this part, we need to introduce a test function. A test function given in this form for the function psi. We take it to some power. This power is something is crucially less than 1, and minus the function phi. Well, the two constants epsilon and lambda are proportional to the given constant a, the normalizing constant a in the power of 1 by n plus 1 or 1. Well, by a straightforward computation, by computing the Laplacian of the weighted Laplacian of the test function phi, well, this is the step where this is the part that we do need this structural condition on the determinant of this guy, on the determinant of the coefficient of gij bar. Well, once we have once we apply the maximum principle to this function phi, we are able to, by suitably chosen constant epsilon and lambda, we are able to show that this test function is always negative or non-positive. So once the function phi is non-negative, non-positive, we have this trivial trivial implication on the functions phi and the solution of the auxiliary equation. And up to this step, we haven't used this alpha invariant type estimate. So we take exponential, first multiply this inequality by some constant beta, and then take the exponential. We get, and then integrate over the level set. And on the right hand side, we are going to get this kind of estimate, this kind of exponential. So if we choose this beta to be sufficiently small, smaller than the alpha invariant, and we will have a uniform control, a free control of the integral on the right hand side. And this is the part where we need this alpha invariant type estimate for the quasi-Flory solving functions. And this is also the effectiveness of this auxiliary equation. Well, once we have that, this is just our Moser, the Schrödinger type inequality. Well, next we just apply some standard LP theory, or like the Holder and Young's inequalities, to derive this constant by setting the k go to infinity. And then elementary from this estimate and also definition of the constant as, we can get this type of decay estimate on the monotone function phi of s. Well, once we have this kind of a decay estimate, then it's a classical fact of Calabi by using the de Giorgi type iteration argument to show that this phi must be 0 whenever the s is sufficiently large. And finally, I just want to mention that this entropy term, this weighted L1 term can actually be controlled by the entropy of the function f. For the Monge-Ampere equation, this just follow, as I mentioned earlier, it's just follow from Jensen inequality and alpha invariant estimate. And for the more general ones, we just apply another auxiliary equation. Originally, we just applied another auxiliary equation and ABP maximum principle that employed by in the work of Cheng. And alternatively, we can also apply another technique of myself and Phong. And finally, I want to I mentioned that this type of auxiliary equation comparison approach by using the auxiliary equations is very versatile. In the past few years, we have developed this approach to get many results in Kähler geometry. Notably, we are able to get some uniform diameter control and a non-collapsing estimate for the Kähler matrix, and plus the Sobolev type inequality, which relies only on the the entropy of the volume form, but independent of the Ricci curvature. So I will just stop here. Thanks.
A very nice talk. So, any questions or comments?
So for the Sobolev inequality you obtained in previous, so are the constant are optimal or?
No. We just get a Sobolev type inequality. The constant, well, we do not expect the constant or the exponent to be sharp, okay, unless you input some constraint on the Ricci curvature. Okay. Because here we only assume the volume. Like the case of Calabi's theorem, we only assume the volume is in L1 plus epsilon. But we can get almost a sharp exponent. We can prove that exponent is arbitrarily close to the Euclidean one, but not achieve it.
Okay. So my second question is, so you said that your estimate actually works for not just Kähler. Is in general Hermitian case.
Yeah.
So is there some constraint on Hermitian metric, like putting balance condition or Godot condition, or just arbitrary Hermitian case?
Arbitrary Hermitian case, because we can only derive the L infinity estimate, not any higher order estimate. For the higher order estimate, you do need this kind of curvature conditions, or you apply integration by parts. You need this extra assumptions on the Hermitian metric, but we only derive the L infinity estimate. In some sense, it's very weak. So well, not only I should also mention that this local comparison approach works not just for emission, but also for this almost complex manifolds, or nearly a complex manifold as well. And even for the remaining manifolds, the approach still works, even though it may not be sharp. Because for the real case, you have the ABP. So
all right, thank you.
Yeah. Any more questions or comments? Probably I have one. So in the beginning of your talk, so you mentioned there are singular differential equation. And singularity, I mean, from differential, it could be regarded as kind of consingularity with angle of 2 pi when beta. And it also corresponds to some of the classification of singularities from birational geometry.
Right.
So does that mean that cone angle could be interpreted as kind of describing?
Oh yeah, the cone angle is the
MMP singularity.
Yeah. Exactly.
So that I mean, if you have the good MMP singularity, then you have some restriction on cone angle, right?
Right. But the cone angle, I think, is much simpler than because the cone angle is along a divisor, a smooth divisor over normal crossing divisor. But for the KLT singularity is only about the discrepancy is strictly bigger than -1. But you know that strictly bigger than -1 means that is integral. It's just L1 plus epsilon. Whenever epsilon is sufficiently small, this integral is still integrable, right?
Yeah,
that's exactly the connection between this analytic analysis and the geometric conditions.
Yeah. Thank you. So if there are no more questions, let's take the speaker again.
Thanks.
Thank you.